The title for the course project is Theoretical and Empirical Understanding of Batch Normalization. And here is the outline of the presentation. We will first introduce batch normalization, followed by the related work and the optimization and the regularization. And the regularization finally is the drawbacks in batch normalization and the related solution. With batch normalization, as shown in the orange curve, convergence speed is faster than that without batch normalization with the same learning rate or more. With batch normalization, we can get better results. The advantage is that we can save training time resources and less experiment times and iteration time. Without batch normalization, it's unable to train a very deep neural network. With batch normalization, we can set a larger learning rate and incentive to network initialization. Batch normalization is a fundamental part in lots of model architecture like inception, rest night, and dense night. Normalization in deep learning has always been a hot topic. Getting normalization right can be a crucial factor in getting your model to train effectively. Batch normalization took the deep learning community by storm, significantly improving the performance of CNNs on image classification and multiple other tasks. Batch normalization is a normalization method that normalizes activations in a network across a mini batch. For each feature, batch normalization computes the mean and variance of the feature in the mini batch. It then subtracts the mean and divides the feature by its mini batch standard deviation. This restricts the activation to have zero mean and unit standard deviation. Batch normalization rescales the normalized activations and adds a constant. However, there are two cases where this might not be a good idea. The first is the small batch size here. If the batch size is only 1, the variance is 0, so batch normalization cannot be applied. Small mini batches make our estimates very noisy and can negatively impact training, meaning batch normalization imposes a certain lower bound on our batch size. The second one is the recurrent connections in an RNN. In an RNN network, the recurrent activation of each time step will have different statistics. This means that we have to fit a separate batch normalization layer for each time step. This makes the model more complex and more importantly, it forces us to store the statistics for each time step during the training. In addition to batch normalization, layer normalization is a kind of normalization method. To understand the layer normalization, consider a mini batch consists of multiple examples with the same number of features. Mini batches are matrices where one axis corresponds to the mini batch and the other axis corresponds to the feature dimension. Batch normalization normalizes the input features across the batch dimension. The key feature of layer normalization is that it normalizes the inputs across the features. The difference becomes clear when we visualize it. In batch normalization, on the left side here, the statistics are computed across the batch and are the same for each example in the batch. In contrast, in layer normalization, the statistics are computed across each feature and are independent of other examples. Well, as for instance normalization, it computes the mean and the standard deviation and normalize across each channel in each training example. It is specific to images and not trivially extendable to RNNs. Instance normalization performs well on style transfer when replacing batch normalization. In layer normalization, the statistics are computed across each feature and are independent of other examples. Normalization has also been used as a replacement for batch normalization in GANs. As for switchable normalization, it's a method that uses a weighted average of different mean and variance statistics from batch normalization, instance normalization, and layer normalization. Similar to batch instance normalization, the weights were learned through backpropagation.
Many experimental results show that batch normalization can accelerate the training of neural networks significantly, and it can also reduce the sensitivity with respect to different learning rates. One intuitive explanation of this property is that batch normalization can make the loss landscape of neural networks much smoother. So one natural question is, how do batch normalization change the loss landscape of neural networks? Here we give a quantitative analysis on how batch normalization changes the loss landscape. Consider the following simple setting, where a batch normalization layer is inserted after a fully connected layer during some training step of the neural networks, and we let L be the loss of the original network and hat L hat be the loss of the normalized neural network. Here is the theoretical result. We can find from the results we can find that the loss the gradient of the loss after normalization will become smaller than the gradient of the loss before normalization. That is, the Lipschitz constant will become smaller after we insert a normalization layer. Uh, Here is the proof of the theorem. First, by some definition, we can calculate the loss after normalization with respect to the unnormalized output, and we can rewrite it into a vector form. Finally, if we denote the average of the gradient by mu g, then we can rewrite the gradient of the loss with respect to the batch yk. Yk is an m-dimensional vector, where each element of vector represents a sample in the batch. So by some trivial algebra, we can conclude that the gradient after normalization will become smaller than the gradient before normalization.
Except for optimization, batch normalization also can prevent overfitting. You can see in this picture, without using batch normalization, its test accuracy is much lower than using batch normalization. The orange curve means the network using batch normalization, and we can see that it has a generalization gap. So why batch normalization can prevent overfitting? One potential explanation is that it has large convergence rate and it can avoid local minima. We can see that, in training data set, batch normalization training accuracy is much higher than without using batch normalization in first training epoch. But later, there are some works that can replace batch normalization with better initialization methods in residual network like ResNet. And we try this method, we can see that with a better initialization method, network without using batch normalization can converge as fast as using batch normalization or even faster than that. However, its test performance still lower than using batch normalization. The comparison is between the orange curve and blue curve. You can see that it's still lower than it with 1 or 2 points. So why, except for convergence rate, what causes batch normalization can prevent overfitting? We can review the batch normalization algorithm. You can see that when we calculate mu b and sigma b, we randomly sample a mini batch data to represent the whole data set. However, when we sample the mini batch data, it has some random, and this random will cause the mu b and sigma b contain some noisy. So we guess that this noisy will let our model can prevent overfitting. So one solution to guess if this causes a problem, we can use a larger mini batch and then keep the and with a larger mini batch, the noise is decreased, and we can keep the background with the same batch size, and to avoid the negative effect other effect from SGD. And so we conduct the experiments. We use different forward sample size like 128, 2015 to 2014A. And we can see that with the increase of sample size, the test accuracy is decreased and the test loss is increased. So with more accurate in estimating the mu b and sigma b, the way that BN prevent overfitting is decreased, and the test performance also decreased. And we can see the test loss curve. It also has the same phenomenon. So we guess that BN can prevent overfitting is when it sample the mini batch and calculate mu b and sigma b, it contains some random and noisy, and this noisy lets our network avoid our network to overfit on training data set.
Hello, I'm Zhou Xiao, and now let me introduce the drawbacks of batch normalization and the related solution. Batch normalization's error increases rapidly when the batch size becomes smaller. Besides, its effectiveness also diminishes when the training mini batches do not consist of independent samples. This limits the batch normalization's uses for training large models and transferring features to computer vision tasks, including detection, segmentation, and video, which require small batches constrained by memory consumption. This also has problems when training with non-IID mini batches. Now let us see the experimental results of the comparison with different batch sizes. We can see that when the batch size is 128 and 8, the batch normalization has a good effect on the test accuracy. It has a better test accuracy compared with that without batch normalization. However, when the batch size goes down to 2, it will have a test accuracy lower than that without batch normalization. We can see from the experimental results that batch normalization is really sensitive to the batch size. It will have unsatisfactory performance when the batch size is really small. Now let us see the first method. Group normalization uses the same formula as that of batch normalization but has a different choice of SI. SI is chosen such that the normalization is performed in the same instance and the same group. Here, G is the number of groups. C divided by G is the number of channels per group, assuming each group of channels are stored in a sequential order along the C-axis. Group normalization computes mu and sigma along the H W-axis and along a group of C divided by G channels. Let us now introduce the second method to reduce the drawback. Mu is an estimate of the mean of x, and sigma is an estimate of its standard deviation, computed perhaps as a moving average of the last several mini batches. Batch normalization augments the network, which contains batch normalization layers with a per dimension affine transformation applied to the normalized activations. The R&D correct for the fact that the mini batch statistics differ from the population ones. This allows the layer to observe the correct activations, namely the ones that would be generated by the inference model. Here, R&D is calculated by the formula sigma b divided by sigma and mu b minus mu divided by sigma. R and D is calculated by the formula and constrained in a region parameterized by Rmax and Dmax. When epoch is larger, the constraint is relaxed. Finally, let us see the experimental results of effects of group normalization and batch renormalization. We can see from the table that when batch size changes, group normalization and batch renormalization perform steadily compared to batch renormalization. We can see that group normalization and batch renormalization alleviates the drawback of batch normalization. Okay, that's all. Thank you for your listening.